In this set of notes, we will be going over propositions and truth tables. So that's what we'll start with this first section. The building blocks of an argument are called propositions. And before we go any further, I feel like we should be defining this word. So a proposition makes a claim. It's either an assertion or a denial. And it may be true or false. So this claim could either be true or false, and it must have the structure of a complete sentence. That is important. So, for example, the sentence, Greg is sitting in a chair. This represents a proposition. That could be true, that could be false. Another way to think of a sentence would be a math sentence. So 3 plus 2 equals 6. This is a proposition, but this is a false proposition. Everybody knows 3 plus 2 is not 6. Next, like an example of something that is not a proposition would be any type of question. Are you going to eat that? I love this question. Are you going to eat that? This is a question, though, and therefore it cannot be a proposition. It has to be a sentence. So now that you have an idea as to what propositions are, propositions have two possible truth values. It's either got to be true or false. There's no in between. A few more definitions and vocabulary that you need before we go on would be the negation of a proposition is another proposition that makes the opposite claim of P. So it is written either not P with the actual word not in front of it, or squiggle P. And this has the opposite truth value of P. So what we can use is a truth table to show each possible set of truth values for the propositions being considered. So if you look down here at this truth table, it's basically like a t-table, and ones that we will look at later will be like an extended t-table or t-chart. We're only going to put truth values in here. So P can either be true or false, but not P will have the exact opposite values. So if P is true, then not P will be false. If P is false, then not P will be true. These have opposite truth values. And again, this could be written as not P. So in this next little section, we have a couple propositions, like legitimate propositions, not just truth values of propositions. We could say, Cameron is a mechanic. Well, the negation of this proposition would be something that says the exact opposite. Like, Cameron is not a mechanic. That says the exact opposite of Cameron is a mechanic. And you can see that when we were looking at P and not P up here, all we had to do was add the word not, and that ends up being true with our propositions down here. For this other one, very quickly, we have 3 plus 2 equals 6. Well, we can write the negation of that as 3 plus 2 does not equal 6. And finally, the last little bit on this page here, I'll give it a little underline to let you know that there's kind of a new section starting here. The double negation, or you may have heard it before as the double negative. So consider the following proposition. It is highly unlikely that Amy wasn't carrying her water bottle with her that day, said Scott. Does Scott believe that Amy carried her water bottle that day? Well, if you look at the double negative that is happening here, it is highly unlikely, so we have one negative here, that Amy was not carrying her water bottle that day. These will undo each other. So if I take a look at this, and I take a look at this, and we cross those out, we can see that it is highly likely that Amy was carrying her water bottle that day. So absolutely, yes, Scott believes that Amy carried her water bottle that day. The proposition not P has the same truth value as P. And it says add not P to the truth table above, but I'm just going to rewrite it right in this area really quickly. So from above, we had this part of the table. But now we have this new column that we're going to be adding to it. Not P, or squiggle P. And it's basically like when you have a negative times a negative in math, they will cancel each other out and it'll become positive again. So this truth value matches exactly that truth value. And the same thing here with the false. The second section that we have here, logical connectors. These are words like and, or, if, then. These logical connectors allow us to join together two or more propositions. So you can see here we have the logical connector and. So if we have two propositions, one P, stating the students went to the Cayman Islands, and Q being another proposition, summer was fun. If we join them together with and, we have the students went to the Cayman Islands and summer was fun. We can join them together with or. We say the students went to the Cayman Islands or summer was fun. And that one doesn't sound right grammatically, but it is a legitimate statement that we can make. The last one that we have here is if then. If the students went to the Cayman Islands, then summer was fun. So we've got these logical connectors that allow us to join two or more propositions to create bigger propositions. So this is just one proposition. This is a new proposition. This is a single proposition now. So we can look down here at and statements. Given two propositions P and Q, the statement with the actual logical connector and, P and Q, is called their conjunction. The conjunction P and Q is true only if both P and Q are true. So we will set up a truth table that looks like this. For our P column, our P proposition, we have to set up two truths and two falses. And that's because when we come over here to the Q, when P is true, Q could either be true or false. And when we set up false, P could either be true or false. So we have four possible combinations here. They could either both be true, P be true and Q be false, both be false, or P be false and Q be true. So when we look at the conjunction of these things, we just got done saying up here, the only time the conjunction is true is if they're both true. So the answer here for P and Q would be true because they're both true. Every other one here would be false. Now there's one more thing that I want to say about this particular conjunction idea before I move on to some examples, is that there's this little notation over here. And just like we had the squiggle to represent not in the previous slide, we have this little, I guess, upside down V to represent the word and in this particular logical connector. So just be aware of that as we move forward. Let's look at some examples. So here we have a couple of examples, and we're going to evaluate the truth of the following statements. Let's see. Cody is the mascot at San Jack South, and, well, there is my logical connector, so I just want to mark that real quick. And all students at San Jack South are rich. So we have two propositions being joined with the logical connector and. Some of you out there in YouTube world may not know this. In fact, some students at San Jack South may not know this, but Cody is in fact the mascot for San Jack South. So this is true. The other proposition we have here is that all students at San Jack South are rich. And that is definitely not true. So we have a true being joined with a false, and if you rewind just a minute, you'll see that truth table or a description of the and logical connector. The conjunction is only true if both propositions are true. So both propositions are not true, so this entire statement is false. Let's move on to the example 2 there. Example 2 says, some teachers are not good singers. And, okay, well, there's my logical connector. And I had to modify this statement here. The second proposition, Kevin Durant played for the Golden State Warriors in 2017. So, some teachers are not good singers. I would demonstrate, but I don't want to embarrass myself. That is absolutely true. And Kevin Durant played for the Golden State Warriors in 2017. That is also true. So this entire statement for number 2 is true. All right, moving on from there, we will take a look at our next logical connector, the or statement. So the word or can be interpreted in two different ways. We have inclusive and exclusive or. The inclusive or means you can have either one or both. And the exclusive or means you could have one or the other, but not both. Maybe you remember growing up as a child and your parents say, well, we can either go do this or this. You weren't able to do both. You had to pick which one you wanted to do. So that's a pretty good way to understand what an exclusive or is. In logic and in math, we assume that or is inclusive unless we are told otherwise. So very quickly, we want to just take a look at a couple examples down here, determining whether or not the or means inclusive or exclusive. So I will buy a Porsche or a Maserati. Now, I don't have money for either of these, but if you did, you probably are not going to buy both of them. So you can either get one or the other. We would call this an exclusive or. And an oil change is good for 5,000 miles or 3 months. And this one we would consider to be inclusive, because it could be one or the other, or if you drive 5,000 miles every 3 months, it's inclusive. It's both. Continuing with the or logical operator, given two propositions of P and Q, we can join them together in the statement with the logical connector or, right here, P or Q, and we call this the disjunction. The disjunction P or true is true pretty much all the time unless both P and Q are false. So I'm just going to set up the same table we had before, true, true, false, false. And again, we have to have two trues because for each true, Q can change. It could either be true or false. And for each false that we have for P, Q could either be true or false. The only time the disjunction, which has this symbol to it, P or Q. The only time it's false is if they're both false. So our answer here would be false, and everything else would be true. Okay, so let's evaluate a couple of these statements that we were sorry, I saw this, that we were looking at down here with the OR logical connector. Cody is the mascot at San Jack South, or, well, there's the connector. And now we know from the last page that this is true. Or all students at San Jack South are rich. And we know that's false, again from the last slide. So first proposition is true. The second proposition is false. The only way an OR statement will be false is if they're both false. So we have one true, they're not both false, so that means this entire statement is true. Now for the second one, you don't know Amy and you don't know Scott, but they are both professors for math, and neither of them is what it says in this statement. So Amy is a famous country singer, that's not true. Scott is a rock star, also not true. We are joining them together with the OR, and that means since they're both false, the entire statement for number 2 is false. Lastly, we have these if-then statements. This is the third logical operator that we will look at, but I'm going to move this up so that I can work more fluidly. All right, so the if-then statements. We say in a statement of the form if P then Q, P and Q are both the propositions. We call this a conditional statement, with P being called the hypothesis and Q being called the conclusion. The conditional if P then Q is true in all cases except when the hypothesis is true and the conclusion is false. So let's set up our normal truth table that we have here. True, true, false, false. Q can be true or false when P is true, or true and false when P is false. So if P then Q, as we state up here, is true in all cases except when P is true and Q is false. So when P is true and Q is false, we get a false statement. Everything else gives us a true statement. And you can see over here on the right side, we have these examples. And you're more than welcome to pause the video to read these for yourself. Now, in addition to these conditional statements being read if P then Q, or if I eat spinach then I am strong, these conditional statements, there are many other ways to show a conditional relationship. P is sufficient for Q. This is another way to say if P then Q. P implies Q. This is another way to say if P then Q. If P is true, it follows that Q is true. And these three all follow the same order. P comes first, Q comes second. Where it can get tricky is if we see these particular wordings is necessary for and whenever. So it would be Q is necessary for P. So you can see the Q and the P are out of order. And then Q whenever P. You can see the Q and P again are out of order from what we are wanting them to be in, if P then Q. And again, there are some examples here of how statements can read. So if I do this 1, 2, 3, you can see that these statements are here 1, 2, 3. And then similarly, this would be statement 4 and 5, and you can see that those are represented down here with the spinach and strength example. The last little bit to this video, we have just some different ways that we can work with conditional statements. We will talk about the converse, inverse, and contrapositive statements. So the conditional statement that we all know and love is like this: if P, then Q. The converse of this would be if you just swap the Q and P propositions, but we still have a conditional statement. So if Q, then P. That is the converse of if P, then Q. Next, we have the inverse, and the inverse is complete negation of the conditional. So you can see here it says if P, then Q. The inverse would be put not in front of P and Q. So the inverse and the conditional are very closely related. You can see they have the P's and the Q's in the same order. It's just the inverse has not in front of both propositions. And the converse and the contrapositive are very similar as well. So Q and P are in the same order, and the difference between converse and contrapositive is that you have not in front of both the P and the Q. And again, you can see some statements over here that reflect exactly how a conditional statement can be transformed into a converse and inverse and a contrapositive statement. All right, I'm going to do a couple examples here just to see if we can find the truth, evaluate the truth of these following statements. And these are only conditional statements. So the conditional statements and this converse, inverse, and contrapositive part here sort of go together. So let's evaluate some conditional statements. So I see my if-then right here, if-then. So if Cody is the mascot of Sanjak South, and remember that proposition is true, then all students at Sanjak South are rich. And remember that proposition is false. So you can either rewind the video, or if you remember, the only time a conditional statement is false is if the hypothesis is true and the conclusion is false. So this entire statement here is false. And with this other statement here, we have if Amy is a famous country singer. Let me underline the logical connector here, if then. Remember, Amy is not a famous country singer, so that is false. This proposition, then Scott is a rock star, that is also false. And if we have a false hypothesis, then the entire statement is true. And down here, example 2, we have I guess a converting question. This is for the given proposition, write the converse, inverse, and contrapositive and determine which statements are true or false. So we are given this conditional statement here: if I'm awake, then I'm alive. And we really just want to see if that's true first. And just think about it. Think about the entire statement as a whole. If I'm awake, then I'm alive. Well, that's true. If you are awake, you are living. So if I'm awake, then I'm alive. This statement is in fact true. If we want to write the converse, inverse, and contrapositive, though, we have to do what I was doing up here. I need to identify what are the P and the Q. So if we look at the if-then, we can then conclude that I am awake will be the P, and I am alive, that will be Q. So if we want to write the converse, remember we just switch the P and the Q. So it would look something like this. If I am alive, then I am awake. Converse, switch P and Q. All right, is this statement true? If I'm alive, then I'm awake? No, absolutely not. It could be false. It will be false. Because I can think of a time that I'm alive but not awake. Generally when I take a nap or I'm sleeping for the night. All right, so this statement is false. Let's look at the inverse. Remember, the inverse is very closely related to the original conditional. Then we just put not in front of our P and Q. Or we negate our P and Q. So it would look something like this. If I am not awake, then I am not alive. And again, I'm going to go ahead and say that's false, because if I'm not awake, that could mean I'm asleep. And if I'm asleep, then I'm alive. Like, that is a really false statement. Lastly, the contrapositive. Take a few seconds, pause the video, see if you can write the contrapositive. I'll get it up here in about 5 more seconds. The contrapositive of this conditional statement would be very closely related to the converse, and I guess you can kind of see that if you have contrapositive and converse. They both start with con. Maybe that's something you can use to remember that they are related. But the statement would be, if I am not alive, then I am not awake. And that is absolutely 100% true. If you are not alive, there's no way you can be awake. So, one thing I want to explain here is that the conditional and the contrapositive are what we call logically equivalent. That means if we were looking at the truth table for both this conditional statement and this conditional statement, they would be exactly the same. The other thing here is that the converse and the inverse are also logically equivalent. I'm going to have to abbreviate with LE because I am out of space. All right, lastly, we have all of these different conditional statements that are given out here in a truth table starting with P and Q, and you can see that this table with the P and Q is set up exactly the same as I've set up all the other truth tables. Oh, and it looks like this should be Q and not P. So we have that, and you can see that this column and this column are exactly the opposite of each other because it says not P. Remember, not just means the negation, so all of the truth values are exactly the opposite. And you can also see that these two truth tables, or these two columns, are exactly the opposite because they are negations of each other. Then you can see we have the conditional here. Conditional. We have the converse, we have the inverse, and we have the contrapositive, and with the logical equivalence of each. So now down here, example 3 and 4, it's asking us to make a truth table for not P and Q. So this not P is a separate thing all on its own. So what we're going to do, or what I'm going to do, is I'm going to set up a truth table like this with P and Q. And way over here to the right, I'm going to write not P and Q. So before I start attacking this column, I want to know what else do I need in order to be successful with this. Well, I need not P and I need Q. Well, I have Q. Q is right here. So what I should do next is figure out, what does the column not P look like? Well, it will just be the negation of the P column. So this should be false, false, true, true. So now I have everything I need. I've got my not P and I've got my Q. It's right here. and my not P, and I'm going to join them with the logical operator and. So since I have my not P and my Q, I don't need P anymore. And in fact, I'm just going to get rid of it so I don't get confused. So what I'm doing now is joining not P and Q with the logical connector of and, a conjunction. Remember, the conjunction is only true if both propositions are true. So we will have a true for this third row, and everything else will be false. And that's it. There are the values for not P and Q. And you should do something like this similar over here for number 4. You want to try P and Q. Your goal is not P or not Q. And you still have to answer that question, what do I need in order to be successful with figuring out not P or not Q? Do I have everything I need here? The answer is no. Figure out what that is. Pause the video, try it yourself. I'll put the answer up in about 5 seconds. So this is what I need to be successful with not P or not Q. I need not P, which is the negation of the P column. I need not Q, which is the negation of the Q column. And since we're joining not P and not Q together with the logical connector of or disjunction, we don't need these columns anymore. So I don't need P, I don't need Q, and I'm just going to cross those out really quickly so I know what to focus on, the not P and the not Q. Now remember, an or connected statement is true if there is a true in any column. So for this one, I see a true in the bottom row, so this entire statement would be true. In the second from the bottom row, there's a true false, so I know that's true. In the second from the top row, there's definitely a true, so I know that will be true. This is the only one that has no true values, and that will be false. So there is my truth table for not P or not Q. I hope you enjoyed the lesson.